7, I'm going to talk about something called conservative and non-conservative forces. Okay, conservative and non-conservative forces. So what exactly are conservative forces? For example, gravitational force is a conservative force. All right, guys, can you see me? Okay, so gravity is a conservative force. Likewise, spring forces, an ideal spring force is a conservative force. For example, in the case of gravity, if I throw an object up, right, when it comes back down at the same level, it will have the same speed. In other words, the kinetic energy is not lost. So if there's no air resistance, this object will go up and come down at the same speed. Okay? So no energy is lost. In the same manner, a spring force, right? You have a spring, all right, and there's an object here, right? If I compress it, if I compress the spring force, if I compress the spring, I move the object here and release it, okay? The moment it's released, it will spring back with the same speed, all right? So what we find in conservative forces is that energy is not lost. It is just converted from kinetic energy to potential energy and then back. Okay, so that's the thing about conservative forces. So in some of the characteristics of conservative forces are, okay, the work done by a conservative force depends, okay, on the two endpoints. And not the path. Taken. Okay, so the work done by a conservative force depends on the two endpoints and not the path taken. In other words, if you have an object here, if I throw it up, all right, it could go, I could take it through any path, all right, and when it comes back at the same level, it will have the same value, right? The other thing about a conservative force is that if you bring it back to the same place where you started from, the total work done, the total work done is equal to 0 joules. Okay. So we find that gravity and spring, among other forces, are conservative. Later on, when you take electricity and magnetism, you will find that electrical and magnetic forces are also conservative. So we know that work done, okay, by gravity and spring forces, the work done is equal to the negative change in the potential energy. What does that mean? Okay, in going up, for example, when I throw an object up, okay, the work done is negative. Okay, so the work done is negative because the force is downwards and the displacement is upwards. The displacement is upwards. So the work done by the weight or gravity is negative. Okay, so the work done by gravitational force or spring forces for that matter is negative. So if if this is negative, if the work is negative, right, that means the change in potential energy. If you have a negative number here, that negative and negative will cancel, and the change in potential energy is going to be positive. In other words, the potential energy is going to increase, okay, in going from here to here. If you drop an object, then the force by gravity and the displacement are in the same direction, and therefore the work done is positive. So if the work is positive, okay, if this number is positive, that means the change in potential energy has to be negative. So the change is negative. That means it has lost potential energy. Okay? So, so we have this formula, work done by any conservative force, okay, can be written in this manner. Okay, this is chapter 7. So much so that for small amount of work done, which I'll call dW, small work done, is equal to minus small change in potential energy. So you do an infinitesimal, you move the object a small distance. Small work done is equal to minus a small change in potential energy. All right? And the small work done, okay, can be written as the force, which is the force of gravity, or or it could be spring, any forces, okay, conservative forces. So I'll call this conservative. It could be gravity or spring. Okay, this is conservative work times dx is equal to minus du. So a conservative force is equal to minus du divided by dx. So if you know the potential energy function and you take the derivative of that function with respect to x, you can actually recover that conservative force. Okay? For example, if you, right, grab, what is potential energy due to gravity? It is equal to mgx. Okay? So what is du by dx? If I take the derivative of this, okay, I'll get the gravitational force. The gravitational force, which is minus of du by dx. If I take the negative derivative of that, I'll get minus mg. Okay? So the gravitational force is negative. Okay? Which is what we have, right? The gravitational force is pointed downwards. All right? So you can actually recover that gravitational force. Let me give you another example of this. Okay? A spring force, the potential energy due to spring, okay, is equal to k 1/2 kx squared. Okay, so this is due to the spring force, or the book calls it elastic force. Okay, EL. So the force due to elasticity will be equal to minus du by dx. And if I take the derivative of that, the 2 comes in front, the 2 and 2 cancels off, and you get minus kx, which is the correct force that the spring will apply on the object. Okay, so if the object is moving to the right, the spring will apply a force on the object to the left, making it negative to the displacement. So if you have a spring, for example, and it is attached to a block, right? If I move it this way, positive x, the force on this object is negative k times x. All right? So these are conservative forces. So by using this formula, okay, for any conservative force, I can recover that force, which is minus du by dx. Okay, minus du by dx. All right. So what is a non-conservative force? A non-conservative force is friction. All right. So in the case of friction, you find that, for example, if I take and push an object, right, on the table, if I push it with the force in this direction, there's a frictional force. So the work done by the frictional force will always be negative, because friction will always oppose motion. Okay, so in going from here to here, that's the frictional force. Okay, so if the displacement is that way, the frictional force is that way. So the work done by the frictional force is negative. What happens if you push it back in the opposite direction and bring it back to the same point, right? Suppose the frictional force here is 2 newtons and the displacement is 3 meters, right? What is the work done? Work done is force times the displacement. The force is negative, right? Minus 2 newtons times 3 meters is what? Minus 6 joules, right? So the work done by gravity is minus 6 joules, 2 newtons. What happens if I push it that way? And now the frictional force is this way, right? It always opposes motion. So the frictional force is pointed in the positive direction. In the positive direction. And the displacement now, right, is where? In the negative direction, minus 3 meters. So what is the work done? It is 2 newtons minus 3 meters, which is what? Work is minus 6 joules, the work done. So in bringing it back to its original position, what is the total work done? The total work is minus 6 minus 12 joules of work is done. It's not zero, okay? In the case of gravity, if you throw an object up, the work done, right? Suppose this object has a weight of 2 newtons and you throw it up a distance of 3 meters, right? What is the work done when the object goes up? 2 newtons that way, 3 meters that way. So the work done by gravity in going up is what? Minus 6 joules, right? Because the force of 2 newtons is opposite to the displacement, right? Now what happens when it falls back to its original position? What is the work done? The work done in this case would be, because it's now 3 meters downwards, right? What is the work done? So the work done by gravity in falling down is what? 2 times 3, because they're both pointed in the same direction. Minus 2 times minus 3 is plus 6, minus and minus, plus 6 joules. So what is the total work done? 0 joules, right? So any conservative force, if the object comes back to the same position, the net work done is 0. Whereas a non-conservative force like gravity, air resistance, you find that the net work done in coming back to the same position is not 0 anymore. It has a specific value. The system loses that energy, minus 12 joules. In the end, the total energy has decreased by a factor of minus 12 joules. Okay? So that's the difference between conservative and non-conservative forces. So conservative forces, the energy can be recovered. And if it comes back to the same point, okay, it will have the same potential energy due to its height. But the total work done in going up and coming down will be 0. Whereas in the case of non-conservative forces, the total work done is not zero anymore, right? You get a value of, in this case, it's minus 12. In other words, the whole system has lost 12 joules of energy. Now, where did that energy go? It goes in the heat. It goes as heat. So if you had a sensitive thermometer and you monitored the temperature, you would find that these particles are moving faster than before. It's a little warmer, okay? And if you could account for all of that energy, if you could calculate all the kinetic energy of all the molecules that are moving a little faster than before, okay, on the table as well as the box, you could account for that 12 joules, okay? So all of that energy is converted to heat, right? Okay, so I wanted to do that because that's chapter 7. So I'm going to start with chapter 8. I never had a chance to go and do chapter 8 and make a video of it. So I'm going to do part of the lecture on chapter 8 here, and I'm going to record it and I'm going to send it to you. And if I can't finish the whole thing, I'll do a second part on this chapter and send it to you. All right. So chapter 8. Okay, we are going to talk about momentum. Right? So if, so what is momentum? We know that Newton's second law. Okay, force F is equal to m times a. Okay, mass times acceleration. The net external force is mass times acceleration, that's the net. And remember, it's a vector sum, all right? It's not regular addition, it's vector addition. So this is equal to m, and what is the acceleration? We know that it is dv by dt, change in velocity over change in time. That's the acceleration, right? I can rewrite this because mass is a constant. For a constant mass, I can rewrite this as dmv over dt. Okay, because mass is a constant, all right? Because otherwise, what happens when you take the derivative of that? You get dm by dt times v, right, plus m times dv by dt, right? But this is zero, you understand? Because the mass doesn't change, all right? So I get the original. So this equals to mass, dv by dt is the acceleration. So you get the original, okay? So I can rewrite this quantity in this manner. And I'm going to define this quantity. I'm going to call it, because v is a vector, this quantity is also a vector. It's called momentum. And I'm going to use lowercase p. Momentum is equal to mass times the velocity. Okay, so momentum is equal to mass times the velocity. In other words, if you have an object, okay, that has a mass of, say, 2 kilograms, moving with a velocity in that direction of 5 meters per second, then the momentum in that direction is 2 times 5, which is 10 kilogram meters per second. Okay, and it's pointed that way. That's the momentum. Okay, so yeah, I can put this arrowhead. All right, so momentum is a vector, right? And just remember, this quantity, which I call momentum, is different. This number points in that direction. What if you throw an object, if you push an object up, okay, or an object is moving with the speed of 2 kilogram object is moving with the speed of 5 meters per second. What is the momentum going to be? The momentum is now 10 kilogram meters per second. Which way? Pointed upwards. Okay, so even though the numbers are the same, because this is a vector, this momentum is different from that momentum because they are pointed in different directions, right? So momenta, not only momentum is a vector, it not only has a number, but also direction. Okay? So coming back, I can rewrite this, okay? Sum of all the external forces. This is external. Now I'm going to, the book keeps writing external to tell you that it's the outside forces, okay? So I may drop that sometimes because it's understood, all right? This is the vector sum of all the external forces is equal to d. What is mv? We call that momentum, p over dt, okay? So this is how Newton wrote his original second law. He did not write it this way. He wrote it this way. Okay. He called this quantity the amount of motion. Okay. He did not call it momentum. We call it momentum today. It's mass times velocity. He called it quantity of motion in a body. All right. So the sum of all the external forces is equal to the change in momentum over change in time. This is one way of writing Newton's second law, all right? Which was how Newton wrote it originally, right? So going back here, if this is a constant, if you add up all the forces and the resultant does not change, if the sum of all the vector forces is a constant, then I can write this. So if this is a constant, okay, then this quantity also will not change, right? Momentum will not change with time. It will remain the same. So I can write the sum of all the external forces, because it's a constant, I can write it as P2 minus P1 over T2 minus T1. Change in momentum over change in time. Okay? If it's as a constant, okay, the momentum does not change. So I can just take the final momentum minus the initial momentum divided by T2 minus T1. Okay, the quantity is a constant. So I'm going to, if I multiply both sides by T2 minus T1, I can write this as some external force, okay, times T2 minus T1 is equal to the change in momentum, P2 minus P1. Okay, I'm going to call this quantity impulse. Okay, and impulse is a vector. This is a vector. This is a vector. Okay, so impulse. So this is called the impulse momentum theorem. So impulse, and I'm going to call it J. Okay, so J is a vector. Okay, so we have what is called the impulse momentum theorem. Which states that the impulse is the force and how long the force lasts. Okay, so impulse is the force, the net force, and how long that force lasts. Does what? It changes the momentum. Okay, so that's impulse momentum theorem. This also is a vector, right? Now, impulse, now I made this a constant. This quantity, if it's not a constant, all right, I can write it this way. So the impulse momentum theorem, the total impulse, that's the force and how long the force lasts, changes the momentum. This is also true if the force was not a constant. For example, suppose the sum of all the forces changed. Okay, it was some function of time. Right? So this changed. All right. So then this is equal to dp by dt. Right? So if I multiply both sides by dt, I get sum of the external forces times dt for a small time changes the potential, the momentum, changes the momentum, right? And if I integrate this, if I integrate it from t1 to t2, this will be an integral from p1 to p2. And so what do you get? You get the integral from t1 to t2, sum of all the external forces times dt is equal to, what is the integral of that? Okay, it'll be p, right? And the integral of that is p2 minus p1, right? So this, okay, is also the same thing that I wrote here, where J, okay, so this is the impulse momentum theorem, where J, this quantity, the force, now remember the force changes, okay, with time. So the total integral, which I'm going to call J, impulse, changes the momentum. So the impulse changes the momentum. Okay, so the impulse changes the momentum. Okay, 1 second at this. Okay. All right. So impulse changes the momentum. So let's look at situations. Now just remember, if this was a constant, you'll get the original. If this didn't change with time, I could remove this outside the bracket and then it will be the same thing, right? External force, integral dt from t1 to t2, p2 minus p1 for a constant. If this number doesn't change, I can remove it out of the integral sign and you'll get t2 minus t1. This integral will be t2 minus t1 is equal to p2 minus p1. All right, you get the same thing. If this is a constant, you can take it out. Okay, this is a constant. Okay, constant. All right, so we come to, so I'm going to use this formula, okay, for situations where it is needed. One example is in the case of what happens. So let me explain. Suppose in a collision, right? You throw a ball against the wall, and what happens? If this is the force, sum of the external forces, okay, and this is time, okay, in that direction, what happens is that the force will increase and then it will decrease. So this is T1 and this is T2. Okay, so the force will go up and come down. In other words, if I throw a ball against the wall, the moment it hits the wall, what happens? Okay, it flattens out. So this is the initial, right, at T1, and then what happens? It becomes really flat, right, in between, and then at time T2, what will happen at time T2? At time T2, okay, it will bounce back, right? It will be going back in this direction, right? At T1 it will hit it, then I'm talking of a rubber ball, right? And it'll flatten out and then bounce back. So that's the time, T1 to T2. You find that the force increases, and then as it's leaving, the force on the ball has decreased. Okay, so so in situations like that, I can define, okay, so this is the area. So when you're taking the integral from T1 to T2, sum of all the external forces multiplied by dt, which is J, is the area. So you're multiplying the force with time, right? You're multiplying whatever forces, you're breaking this into small pieces, and you're multiplying this with this. You're assuming that the force is constant for that small time. Then for this interval, delta t, dt, you're multiplying the force there, you're multiplying the force, whatever force is there, and you're getting these areas, right? So this integral is just the total area. Okay, it's the total area. If I know, and this is equal to what? P2 by minus P1, momentum before minus the momentum after, mass times velocity, right? If I know this number, now this is very difficult to find, right? Because the force changes. You don't know what this function, unless you know this function is properly defined, right? It's very hard to find this, but I can find this. See, that's the beauty of the impulse momentum theorem. I can find the momentum before, right? Because I know the mass of the object and I know the speed. I know the mass of the object and I know the speed before. I know the speed after. So I can find P2, m times V2. I can find P1 because I know the mass of the object and the velocity, V1. So I can multiply the two. I can get these two numbers, and that will give me this answer, right? In other words, I can, once I get that answer, by the way, this is the change in momentum, right? That symbol means change, okay? I can define a constant force, F, okay, times T2 minus T1. I know the time here, I know the time there, and I can find the average force, which is equal to that. So how do you find the average force? F average is equal to change in momentum, and this is change in time, divided by the change in time. I can find that average force. That average force, okay, that will be the average force from T1 to T2. F average. Okay? So I can find that average force if I know this. Okay, and divide it by T2 minus T1. And that average force, the area of that average force is this. This is the area of the average force. These two areas, this is the area in red. This is the area in blue. And because these two are equal, the area from T1, this area is equal to this area. Okay, the way I've defined it. So if I know P1, if I know these quantities, P2 minus P1, I know the times, okay? I can find the average force. That will give me the same area, the same impulse, because this is the area under the curve, okay? So this is the area under the curve. And this also will give you the same area under the curve, right? So in chapter 8, we use momentum because more often than not, it's very hard to know what these forces are. The forces change, but we can find the final momentum, we can find the initial momentum, and we don't have to worry about these forces, okay? All we need to know is these two numbers, all right? And that gives us the impulse, okay? The force multiplied by time, all right? So let's use this in certain examples, okay? One example would be, for example, if you have an airbag, right? This is your head. Right? You're driving a car. This is a steering wheel, right? And let's say the steering wheel does not have an airbag. So your head is moving at a certain speed, and let's say you get into an accident, and after the accident, all right, this is your steering wheel and whatever is left, right, of you, right? So in both cases, right, so this is the mass of your head, okay? You have a certain momentum, this is the mass, and the velocity now is 0. So you can find the change in momentum here. In both, so this is one situation. What happens if you have, okay, this is the mass, and this is the velocity v, all right? And what happens if your steering wheel has an airbag? Okay. The moment you get into an accident, the airbag comes on, right? This is the airbag. This is your head, which is protected, right? You may be a little black and blue, but that airbag comes on from the steering wheel, okay? The steering wheel may have crumpled, but the airbag comes on and your velocity goes to 0, okay? And this is the mass. So you go from the same speed to 0. So the change in momentum is the same in both cases. Change in momentum, which is P2 minus P1, is the same, okay? This is P2. P2 is 0 minus P1, which is m times v. The same thing applies here. So the change in momentum is the same. But what is the difference? Remember, the change in by impulse momentum theorem, I'm going to take this as a constant, the average force, and T2 minus the time, right? In the first case, this number is the same, okay? In the first case, same change in momentum. What's the difference? The time in which your head comes to a stop is very small. And therefore the forces on your head are going to be large. The average forces on your head. What about the second case with the airbag, right? This is the airbag that comes on, right? What happens? The same change in momentum. Your head goes from the same speed to 0. But now the airbag inflates, and so the time in which your head comes to a stop is large. And therefore the forces on your head are going to be smaller, right? So the same change in momentum, but one, because you have increased the time in which your head comes to a stop, the forces are smaller, right? So let's go. Is that clear? Okay. So we have come across two theorems so far. One was the work energy theorem. So let me write in chapter 7, we talked of the work energy theorem. Actually, chapter 6, work energy theorem, which states that the net work done, or the total work done, W, total, changes the kinetic energy, right? So that was the work energy theorem, chapter 6. Chapter 7, we talk of the impulse momentum theorem. And the impulse momentum theorem states that the impulse, which is the force and how long the force acts, does what? Changes the momentum, right? So what's the difference between the two, right? We know that kinetic energy is 1/2 mv squared and momentum is m times v, right? So what's the difference between momentum and kinetic energy, right? In order to understand that, suppose you have an object that has a mass of 0.5 kilograms. Okay, 0.5 kilograms. Okay, and you throw it with the velocity of 4 meters per second. Okay, so let's see. Yeah, let me use the numbers in the book, all right? So that when you read the book, you have the same numbers. All right, yeah. So you throw an object, a 0.5 kilogram object, you throw it at 4 meters per second, right? And this, what is the momentum? The momentum here is 0.5 times 4, which is, let me see, the book gives, 0.5 times 4, which is 2 kilogram meters per second, right? So this is 2 kilogram meters per second. What if you have an object that has a mass of 1 kilogram, right? And you throw it with the speed of 20 meters per second. Can you see the momentum here, all right, is also, so I throw this object at you, okay? This is a mass object with a smaller mass. The mass times velocity is the same. So in both cases, the change in momentum is the same. The momentum goes from 2 kilogram meters per second, and when it hits you, it comes to a stop. The momentum goes to 0. So the change in momentum in both of these cases is similar, right? But so if the change in momentum is the same, after it hits you, the change in momentum is the same, the impulse is what? The impulse is the average force and how long the force lasts, right? So in both cases, the average force is going to be the same because the time of impact is the same. The change in momentum is the same. The time of impact is going to be the same. It'll come to a stop in the same period of time. So the average force is going to be the same, right? But what about the kinetic energies? The kinetic energies, this one, the kinetic energy, 0.5 kilograms times 4 meters per second, right? And if I find the kinetic energy, it's 1/2. The mass is 5 kilograms times 4 meters per second squared, right? So this is 0.5. Okay, and so if I multiply this out, 4 times 4 is 16. Okay, half of 16, 0.5 is half of 16 is 8, and half of 8 is 4. So the kinetic energy is 4 joules. Okay, when it hits you with a kinetic energy of 4 joules. What about the 0.1 kilogram mass? What would be the kinetic energy? Okay, 1 kilogram, right? You throw it at 20 meters per second. So what do you get? 1/2 times 0.1 kilograms times 20 meters per second squared, right? So 20 times 20 is 400. 1/10 of 400 is 40. Half of 40 is 20. So here the momenta are the same, but this kinetic energy is going to be greater. Okay, the kinetic energy with which the smaller one hits you, it's going to have a greater amount of kinetic energy. And what does that mean? Greater amount of kinetic energy would be, remember, work is what? The average force times the distance. right? F dot S, right? So if this 20 is 5 times greater than 4 joules, so in this case, the distance, okay, the ball will move when it hits you, or if you catch it, right? In both, for example, if you catch this ball and this ball, the time of impact is going to be the same. But the energies, okay, this is 5 times greater. So the average force is going to be the same, but your hand is going to move 5 times further back. So if I catch this ball, okay, my hand will move a certain distance. If I catch this ball, okay, this ball, my hand will move 5 times further back, okay, to accommodate this 20 joules. Does that make sense? So to bring the amount of energy to 0, right, you would apply a force of a certain force, average force, and this will move 5 times further back. Your hand will move 5 times further back compared to 4 joules. All right. So if you're given a choice, which ball should I catch? They both have the same momenta, okay? But the smaller mass ball, because it's traveling faster, would have a lot more energy, and therefore it will push your hand a lot more further behind, right? So that is the difference between the two, right? So they both have the same momenta, but the energies are going to be different. Okay, this is 5 times larger. And because, so if they have the same momenta, the average force is going to be the same, right? In both cases, right? But this, in catching this ball, your hand will move 5 times further, okay, to get to 20 joules. All right, let's do some problems based on the impulse momentum theorem, right? So the impulse momentum theorems, suppose I have an object. So we'll start with simple problems, right? I throw an object. Let's say this has a mass of 2 kilograms, okay? And it is moving at 3 meters per second, okay? And this object, this is the velocity in the x direction, all right? Now remember, gravity will pull it down, right? So it'll hit the wall and it'll bounce back. And let's say it bounces back with the speed of 2 meters per second, right? The velocity in the x direction. The y velocity, remember, it falls down, so it will have a y velocity. I'm just talking of the velocity in the x direction, right? So I can, so what is, so this will give me the initial momentum. This will give me the final momentum, all right? I want to find the change in momentum, right? Let's say the time of impact is generally, you know, if you throw a ball against the wall, the time of impact is somewhere around there, 0.01 second, 1/100th of a second. Okay, now remember, when I talk about the time of impact, it's when the ball hits the wall, right? And then what happens? The ball flattens out, right? And then it bounces back, right? So this is the time of impact. This is the time that I'm talking of, where the forces act, all right? So it's not the time for it to go from there to there and back. No, it's the time in which the forces act. When it hits the wall, there's an impact force. Once it leaves the wall, there's no forces, okay? So with that, let me see. Suppose I want to find the force on the ball, okay? Suppose that's the question. What's the force on the ball? What's the force on the wall at impact? This answer will be the same, right? If the force on the wall is 100 newtons, the force on the ball is 100 newtons, the force on the wall will be minus 100 newtons. You understand? It'll be the opposite. Or if the force on the ball is minus 100 newtons, the force on the wall will be plus 100 by Newton's third law. They are equal and opposite, right? So let's try to figure this out, all right? So what is the momentum here? It's 3 times 2, which is 6 kilogram meters per second. And that is plus because it's moving that way. Okay? What is the momentum of this? 2 times 2, which is 4 kilogram meters per second. And it's minus because it's moving to the left. Okay? So it's minus. Okay, what is the change in momentum? The change is final minus the initial, right? So what is the change in momentum? What is the final momentum? 4 minus 4 kilogram meters per second. Okay, because it's traveling to the left. What is that? Plus 6 kilogram meters per second. So what is the change in momentum? So this answer, okay, I'm going to write it here. What is that? Minus 4 minus, this will be minus 6, minus 10 kilogram, oops, minus 10, not minus 6. Okay, so it's going to be minus 10 kilogram meters per second. Okay, and remember by Newton's second law, how he wrote it? The average force is equal to the change in momentum over change in time, the average force. Okay, the instantaneous force, of course, is dp by dt. All right, if you want to find the instantaneous, this is the average force. Okay, so what is the change in momentum? The change in momentum is minus 10 kilogram meters per second. And how long does the force last? Okay, 0.01 second, right? And so if I divide 10 by 0.01, I'll get minus 1,000 newtons, because this is kilogram meters per second per second. Okay, meters per second is acceleration. So it's minus, yeah, yeah, negative 1,000, right? And by Newton's third, so that makes sense, because when the ball, right, hits the wall, the force that is the wall will push the ball that way, right? Negative, in the negative direction, in that direction. So that's minus 1,000. By Newton's third law, the force on the wall will be plus 1,000 newtons. Okay. So I can find the average force, even though I don't know the forces. The forces change here, right? The average force, if I know the time of impact, I can find the average force on the object. All right. Okay, so let's go to an important topic, and then we will I'll do a problem and we can close for the day. All right, so it's called conservation of momentum, and conservation of momentum problems are going to be many. All right, so conservation of momentum, so it's called conservation of momentum. Okay, and many times we don't know what the interact forces are. It's very hard to use chapter 5 in many situations. But the impulse momentum theorem, okay, using the impulse momentum theorem and conservation of momentum, we can do a lot of problems where the forces are unknown. For example, when a ball hits a wall, the force goes up and then goes down, right? I mean, it's a complex situation, all right? So what do you do in that case? Well, we can use, if I know the change in momentum, okay, and I know the time of impact, I can find the average force in many problems, right? and so on. I can also calculate, if I know the impulse, I can calculate the momenta, all right? So let us talk of, okay, so momentum. So suppose you have two astronauts in space, all right? So as good as I can draw, they're floating in space, all right? And there you have another astronaut here, he's floating in space, okay? Okay, and they push on each other. Okay, they push on each other. Okay, can you see by Newton's third law, action and reaction? So I'm going to call this A, I'm going to call this B. I'm going to call this B. Okay, and I'm going to write the force, okay, of B on A, okay, is equal to by Newton's second law. This is change in momentum divided by the change in time. So the force with which B pushes on A, this is FB on A. Okay. What about the force by Newton's third law, the force A on B? A applies on B. Okay, so F A on B, okay, is equal to the change in momentum of B divided by dt. Okay, and I know that F B on A is equal and opposite, because these two are in the opposite direction. To point it in the same direction, I'll have to put a minus sign, is equal to F A on B. Okay, that is needed. Remember, this is a vector. This vector is pointed that way. This vector is pointed this way. So if I want to make them equal, right, I'll have to put a negative sign to make this vector flip over. Now they are pointing in the, so they'll be equal. So if I add the two forces, if I bring this on this side, I'll get FB on A minus FA on B is equal to, right, is equal to 0. So what does that mean? FB on A, right, is dPA over dt, okay, plus dP, the change in momentum of B in time, is equal to 0, right? And hence I can write, okay, by the way, this this is minus, right? But I can, this will be pointed that way, so I can write it that way, right? This is pointed, this is negative, it's pointed in the negative direction, this is pointed in the positive direction. So I can write the change in momentum of A and B with respect to time t is 0, right? So, by the way, we call these forces internal forces. If I push on something at the...
Wouldn't it have to be...
Pardon?
FB on A? Wouldn't it have to be FB on A plus FA on B?
Yeah, but this gives you the directions, right? So this is the change in momentum of that change in momentum of B, right? They are in the opposite direction. So what does that mean? If I push on something, that something will push me back with an equal and opposite force. Okay, those are internal forces. Okay, so in this system, if I look at this two astronauts, those two forces are internal. External forces, for example, if I'm only looking at B, then this becomes an external force on B. Okay, but if I'm looking at the two of them, the total system, okay, these two forces now become internal. All right, so I can write, so what does that mean? The change in momentum with time is 0. In other words, this number does not change. Remember, the derivative of a constant is 0. So that means this is a constant. Okay, so implies, this is the symbol for it, implies that the total momentum, momentum A plus momentum B, okay, is a constant, a number that does not change. Because if you take the derivative of that, that will give derivative of a constant is 0. Okay, right? The slope of a constant is 0. So that brings us to a very important theorem. If there are no outside forces, if there are no outside forces, okay, if there are no outside forces, the total momentum before, or the total momentum remains the same. It does not change, which means, okay, the total momentum before is equal to the total momentum after. Okay, the total momentum before is equal to the total momentum after. So we call this is called conservation of momentum. Okay, conservation of momentum. And a lot of problems are going to be based on this. You're going to find the total momentum before, the total momentum after, and we're going to use this. Okay, this is conservation of momentum. This I can apply to situations. I just showed two forces. You could have, in a system, you could have objects that hit each other, right? There are more than one system. And if I will find, for example, if this is moving with a velocity v1, this is m1, this is m2, moving with a velocity v2, this is m3, moving with a velocity v3, this is m4, moving with the velocity v4, and so on, m5, moving with the velocity v5. I find that the total momentum before, if there are no outside forces, the total momentum is conserved. That means the total momentum will always be the same. In other words, remember they are vectors, all right? So the momentum of this, let's say, is pointed that way, m times v1, plus the momentum of that, say, is pointed that way, m times v2, plus the momentum of this, which is m times v3, is pointed that way, right? Pointed that way. So you add up all the vectors and you get the total momentum. What we find is that the total momentum before will always equal the total momentum after. So after you add all the vectors, let's say the momentum before, the total momentum before was pointed that way, okay? If there are no outside forces, say 1,000,000 years from now, you come and look and you decide, let's find the total momentum. Let's add, remember, they bounce, they hit each other, right? And they bounce around, and you decide, let's find the total momentum. And you add all the momenta, and you will, if there are no outside forces like friction, etc., you'll find that the total momentum before is equal to the total momentum after. It will have the same magnitude, that means the same size arrow, and it will be pointed in the same direction. All right? So we call this conservation of momentum. Okay? The total momentum before is equal to the total momentum after. If there are external forces, if there are outside forces, then the momentum will change. Okay? So if there are outside forces, okay, plus the internal forces which we talked about, this, if this is not zero, then dp by dt is not zero. The momentum will change. Okay? If the sum of all the external forces equals zero, of course, internal forces are always going to be equal to zero, okay, in the system. But if the sum of when you add all the external forces, if that is zero, okay, then the change in momentum is going to be zero. dp, the total change in momentum, is going to be zero. That means the total change, this quantity does not change, it's a constant. The total change in momentum. So the conservation of momentum states that if there are no outside forces or the external forces are zero, we can say that the total momentum does not change. All right? Let me give you, so we are going to use this principle in one of the situations where we are going to use this principle is, we are going to use this principle in what we call collisions, right? So there are two kinds of collisions. Okay, there are two kinds of collision. The first is elastic. Okay, and the second is inelastic collision. Okay, in both cases, the forces are internal. If something hits something, they will hit each other. The forces of when on impact, right, they will hit each other and the forces will be equal and opposite, and therefore, okay, momentum is conserved. Momentum is conserved. That means the total momentum before is equal to the total momentum after. So here also the momentum is conserved. Right? So as long as the impact forces are large, momentum is also conserved if the impact forces are much larger than the frictional forces. So even though there may be outside forces for collisions in particular, okay, the collision forces are generally much larger than the frictional forces and air drags. So we find we can use conservation of momentum for collisions, okay, because we can ignore the outside forces. We can say they are, compared to the impact forces when things collide, the frictional forces are negligible, all right? So we can ignore that frictional forces and use conservation of momentum. So both for elastic and inelastic collision. What is an elastic collision? An elastic collision is a collision that occurs and the total kinetic energy before is equal to the total kinetic energy after. Right? That generally happens in conservative forces. We have talked of conservative forces when, for example, suppose there's a spring, right? For an ideal spring, right? Suppose I push an object against the spring. I push it. It has a velocity v. what will the object do? It will compress the spring, right? And when it comes back, it will have the same speed, same velocity in the opposite direction. Okay? But the kinetic energy before and kinetic energy after collision are the same, right? So if there are no frictional forces, the total kinetic energy before and after are the same because it'll come back with the same speed. So generally in conservative forces are generally elastic in nature. Okay? Even pool, in a pool, for example, if a 6 ball collides with an 8 ball, okay, this may deform slightly and then bounce back. So in a pool table, the collisions are more or less elastic. There may be slight deformations where, dents, but generally, by and large, the denting is very small. Okay, so not a lot of the energy is absorbed. So when they hit each other, they bounce back, okay, at more or less the same speed. So we can say on a pool table, the collisions are more or less elastic. Inelastic collisions are when something hits and bounces back at a smaller speed. Okay, that means the kinetic energies are not equal. So in an inelastic collision, okay, the kinetic energy before is not equal to the kinetic energy after. Okay, so in an inelastic collision, okay, the kinetic energy before and after are not the same because it's going to hit something and bounce back at a smaller speed. Okay, so we call that an inelastic collision. But in both cases, the total momentum before, because the forces are internal, in both cases, momentum is conserved, whether it's elastic or inelastic. What is not conserved is kinetic energy. In an elastic collisions, kinetic energy before and after are the same, okay, because they bounce back at the same speed. In an inelastic collision, the kinetic energy is not conserved because when something hits something, it bounces back at a smaller speed. So some of the energy is lost in the collision, right? So we call that inelastic. And if something sticks to something, you throw at something against, for example, if I take, say, some soft object, right? A wet object and throw it against the wall and it sticks. That collision is perfectly inelastic collision. So it belongs to this category, okay? If the colliding objects stick, then the collision is perfectly inelastic. Perfectly, perfectly inelastic. Okay? So if the colliding objects stick, then the collision is perfectly inelastic. So it belongs to this category, except the object hits something and sticks, right? For example, sometimes, you can have, so let's look at certain situations, all right? So for example, if an object here, right? I throw an object here. Remember when I threw this object and it bounced back at a smaller speed, right? So the kinetic energy before and after are not the same. So this collision in the first example was inelastic, right? So if you're sitting on the wall, right, you'll see the object come at a certain speed and bounce back at a smaller speed. What if they bounce back at the same speed? Okay, now this collision is elastic Because you see, because the kinetic energy before and after are the same, right? If this mass is 2 kilograms, this mass is 2 kilograms, what's the kinetic energy before? The kinetic energy before, it's 2 or 1, right, is 1/2 m, which is 2 kilograms, times 3 meters per second squared. You square that, right? So 2 and 2 cancel, so what do you get? 9 joules, right? What's the kinetic energy after? 1/2, 2 kilograms, 3 meters per second, minus 3 meters per second because it's going to the left. But if you square it, it becomes positive, right? Minus 3 times minus 3 is 9. There's 2 and 2, so this is going to be 9 joules. So the kinetic energy before and after are the same. And this collision is now elastic, right? But if it was this, if this was 2, what will this become? This is minus 2 squared, minus 2 meters, right? So 2 and 2 will cancel. Minus 2 times minus 2 is 4 joules. Now the collision is inelastic, right? Does that make sense? And if it sticks, okay, if I throw this object and it sticks, that means the velocity after collision is 0, right? So what is the total kinetic energy? Before it's 9, after, because it sticks, this is 0 meters per second. So the total kinetic energy is 0 joules. So the numbers are not equal. So this also is inelastic collision.